Hello everyone and welcome back to Educator.com. In this lesson we're going to talk about ramps and inclines. Our objectives include drawing and labeling free body diagrams showing all forces acting on an object on a ramp, drawing pseudo-free body diagrams showing all components of forces acting on the object, and utilizing Newton's laws of motion to solve problems involving objects on ramps. So we've done a few of these already, but I think it's worthwhile to really take some time and make sure we've got these down because they come up so commonly. So, drawing free body diagrams for ramps. Choose the object of interest and draw it as a dot or a box. Draw and label all the external forces acting on the object, and then sketch a coordinate system choosing the direction of the object's motion as one of the axes. That means your x-axis might be tilted in some direction. That's okay. For the case of an object on the ramp, the direction of the object's motion should most likely be up or down that ramp. So if we have something like a ramp with a box on it, physicists seem enamored with boxes on ramps for some reason. At some angle theta, there's our box. What I would do to draw my free body diagram is I'm first going to draw my axis at the same angle as the incline of the ramp. So I would call that my x-axis. Then I'll do my best to draw a line perpendicular to it for my y. So there's x, there's y. We'll draw a dot for our object. We'll have our normal force perpendicular to the plane of the ramp. We will have our frictional force. In this case, assuming it's sliding down the ramp, we'll oppose that. So we'll call that our frictional force. There's our normal force. And weight straight down. And that would be our free body diagram. Now, when the forces don't line up with the axes, we can draw that pseudo-free body diagram where we break some of those forces up into their components. Then we redraw our diagram with all forces parallel to the axes. So if we had something like, well, let's draw it again, our free body diagram with our axes, x and y, and I'm just going to show how the angle of our plane is the same as the angle of our ramp there. We had a frictional force, we had a normal force, and we had weight down. If that angle's theta, then this angle also is theta. We're going to break mg up into components that are parallel to the y-axis and parallel to the x-axis. So the way we do that is with our pseudo-free body diagram on a separate diagram. If we want all of our points on the AP test, I'm going to draw our axes again. X, y. We have our dot. We still have our frictional force, our normal force, but now we put in our components of weight. We have the component that's adjacent to our angle, which I call mg perpendicular because it's perpendicular to the plane of the ramp, is mg cos theta, and mg parallel, the component of the weight that's parallel with the ramp, is mg sine theta, where again, theta is the angle of your ramp itself, or it's also that angle right there. All right, so boxes on ramps. Draw the forces, the free body diagram, and the pseudo-free body diagram for a box sitting on a ramp of angle theta. Then write Newton's second law equations for the x and y directions. All right, well, as we take a look here, let's start by drawing the forces on our box itself. Normal force, we'll have a frictional force, and mg. Can't ever get too much practice doing this. We'll draw our free body diagram over here. We would have normal force, N, frictional force, opposing motion, and mg. And separately, again, separate diagram, can't emphasize that enough. our pseudo-free body diagram. X, Y. There we go. We've got our frictional force, our normal force, and now breaking up our weight into a component parallel, mg sine theta, and perpendicular, mg cos theta. And if I were to write Newton's second law equations there, in the x direction, net force in the x direction, assuming we're going to call down positive here, we could write that as mg sine theta minus frictional force equals max. And in the y direction, net force in the y equals n minus mg cos theta, which is equal to may, but the box is sitting on the ramp. It's not going to accelerate off the ramp, nor is it going to fall through the ramp anytime soon, so that's all equal to 0. So that would work. Let's do an example here. 3 forces act on a box on an inclined plane as shown in the diagram below. Weight, friction, normal force. If the box is at rest, the net force acting on it is equal to, if it's at rest, the net force must be 0, an equilibrium condition. So our answer there must be 0 because the box is at rest. Let's do another one. A 5 kilogram mass is held at rest on a frictionless 30-degree incline by force F. What is the magnitude of force F? Well, let's start with our free body diagram. I'll put it up over here. There's our x. Perpendicular to it, we'll draw our y. So x, y. We have our normal force. We have our applied force F and mg straight down. So I'm then going to draw our pseudo-free body diagram. Let me put that over here on the left where we've got some room. Our pseudo-free body diagram. There's our x. There's our y. We still have our normal force along the y. We have our applied force. But mg we break up into components. We've got the component parallel to the ramp, mg sine theta, and perpendicular to the ramp, into the ramp, mg cos theta. All right, let's call this our positive x and that our positive y direction. So when we write our Newton's second law equation, let's start in the x. Net force in the x direction is going to be F minus mg sine theta, which is going to be equal to max, which, since acceleration is 0 because it's at rest, is all equal to 0. Therefore, F equals mg sine theta, which is going to be 5 kilograms times our g, 10 meters per second squared, times the sine of 30 degrees, which is 1/2. So half of 50 is going to be 25 newtons. All right. Let's take an example where we look at a truck on a hill. The diagram shows a 100,000 Newton truck at rest on a hill that makes an angle of 8 degrees with the horizontal. What is the component of the truck's weight parallel to the hill? Oh, mg parallel, if we just remember that equation, the component of the weight down the hill is going to be mg sine theta. It gives us the weight mg already, which is 1 times 10 to the 5th newtons, times the sine of 8 degrees, which is right about 1.4 times 10 to the 4th newtons. Answer 3. All right. Force up a ramp. A block weighing 10 newtons is on a ramp inclined at 30 degrees to the horizontal. A 3 Newton force of friction, FF, acts on the block as it is pulled up the ramp at constant velocity. Ooh, always important to know constant velocity. Net force must be 0, acceleration is 0, with some force F, parallel to the ramp. Find the magnitude of force F. Well, let's start with our free body diagram. I'll draw it over here on the left to begin with. Got x and y, and our object, a dot. We have a normal force. We've got some force F up the ramp. We have our frictional force, and we have the weight of the box, which it gives us is 10 newtons, always down. So now we can draw our pseudo-free body diagram. We'll do that over here on the right. Y, X. All right. F still acting up the ramp. N perpendicular to it. Force of friction down the plane of the ramp. And we're breaking up mg into its components. We have the one perpendicular to the top of the ramp. That's going to be 10 newtons cosine 30 degrees, which I believe is 8.66. We'll have 10 sine 30 down the plane of the ramp parallel, which is going to be 5 newtons. So what is the magnitude of force F? Well, let's use Newton's second law in the x direction. F net x equals, we have F minus the force of friction minus 10 sine 30 has to equal 0 because it's not accelerating. It's at moving at constant velocity. Therefore, F equals force of friction plus 10 sine 30, which is 5, which is our force of friction, it says, is 3 newtons. So that's 3 newtons plus 5 newtons. Therefore, F must be equal to 8 newtons. All right, let's take a look at some acceleration down a ramp. A 100 kilogram block slides down a frictionless 30-degree incline as shown. Find the acceleration of the block. All right, just like we've been doing, let's draw our axes for a free body diagram. There's our X. There's our Y. There's our box. It's on a frictionless surface, so we have normal force, and we have its weight down. No friction, no applied forces. So let's do the pseudo-free body diagram. Looks like we've got room right beside it to do so. So we'll draw our pseudo-free body diagram over here. We still have our normal force up the ramp, but we're going to break mg into components. We have mg sine theta parallel with the ramp, and mg perpendicular, which is mg cos theta, perpendicular or into the plane of the ramp. There's our y, there's our x. So if we want the acceleration of the block, it's going to accelerate in the x direction, so I'm going to write that Newton's law equation first. F net x equals, well, the only thing we have there is mg sine theta, which must equal m times acceleration in the x direction. Therefore, pretty straightforward, acceleration in the x direction is just g sine theta, which is going to be 10 meters per second squared, sine 30 degrees. Sine 30 is half, so that's just 5 meters per second squared. All right. Let's talk about what happens when we place a block on a ramp with an unknown coefficient of friction. The angle of the ramp is slowly increased until the block just begins to slide. You can find the coefficient of static friction is a function of the ramp's angle of elevation, because the angle where the object just begins to slide is known as the angle of repose. So you keep lifting that up. When it just starts to slide, you measure that angle, and you can find out the coefficient of friction. So let's see how we could do all that. Here's a free body diagram of our block on the ramp. We have the force of static friction holding it in place, the normal force out of the plane of the ramp, and its weight down. And we're going to lift it up until that angle is right at the point where the box just begins to move. Right there. And then we can draw our pseudo-free body diagram, just breaking up mg into components parallel and perpendicular to the ramp, as shown. Now, if we want to find the coefficient of friction, we'll start by writing Newton's second law in the x direction. net force in the x direction is going to be, well, we have that force of static friction minus mg sine theta, and all of that must be equal to max, but right at the point where it's just barely beginning to move, that acceleration is 0. So therefore, the force of static friction is equal to mg sine theta. Let's do the same basic analysis in the y direction. The net force in the y direction is going to be our normal force minus mg cos theta, and all of that equals may, but ay is going to equal 0. The box isn't going to spontaneously fly up off the ramp or go through it. Therefore, we can write that the normal force is equal to mg cos theta. Putting all of this together then, remember friction is fun. Force of friction equals mu times the normal force. That means that mu, our coefficient of friction, must be the frictional force over the normal force, which is mg sine theta over mg cos theta, m over m, g over g. Sine theta over cos theta is the tangent of theta. So, if you want the coefficient of friction, lift it up until the object just barely begins to slide, measure that angle, and the coefficient of friction is the tangent of that angle. How slick is that? All right, let's take a look at one more sample problem. Jane rides a sled down a slope of angle theta at constant speed v. Constant speed. Right away, A equals 0, net force equals 0. Determine the coefficient of kinetic friction between the sled and the slope. Neglect air resistance. Okay, let's draw our free body diagram. There it is. We'll call this our plus y, and that's our plus x direction. There's our object, Jane and sled. We have a normal force out of the plane of the hill. We have mg, force of gravity down, and some force of friction opposing motion. All right, from there we can do our pseudo-free body diagram. Let's put that over here on the right. Here we have our positive y, positive x. We still have our normal force. We still have our frictional force. And mg we're going to break up into components. We have mg sine theta parallel to the ramp, and mg cos theta perpendicular to it. So now we'll go to Newton's second law. Let's look in the x direction first. F net x is equal to, we have mg sine theta minus our force of friction, and all of that is equal to max, which is equal to 0 because it's at constant speed. Therefore, force of friction equals mg sine theta. And if we look in the y direction, net force in the y direction equals n minus mg cos theta equals 0. Therefore, n equals mg cos theta. So the coefficient of friction is the frictional force over the normal force, or again, mg sine theta over mg cos theta, which is just tangent of theta. Almost the same thing you just did. Why is that? Well, before, when it's just barely beginning to move, on that previous problem to find the coefficient of friction, it had a net force of 0. That was right at the point where everything's still balanced. Same idea here. You're at constant speed, net force is 0. It's the same analysis, just from a slightly different perspective. So this is really an angle of repose question because it's moving at constant speed. All right, hopefully that gets you a little more confident and feeling good about these ramp and incline problems. Thank you so much for watching Educator.com. We'll see you soon. Make it a great day, everybody.